Now we want to see some examples of what we have learned so far. Now, in this case, we want to find the coordinates for the point B. So here we are given a line, straight line, y equal to x plus 4. We are given this point, and this point here we are given, but we can also figure it out because it has x coordinate 0. And this means where it crosses or intersects the y-axis. So this must be 4. So given A and C and all this information, and that the green line here is a normal to the red one, can we find the coordinates of B? Let's look at one possible solution, so one alternative solution. Let's call it alternative solution 1. And here we will use a normal. The normal will be central to our solution. So we see that the normal, what is the slope of the normal? The slope of this one is 1. So the slope of this one must be 1 divided by 1, but that's just minus 1. So this is minus 1 times x. But we can also write that just as minus x plus some constant here. Let's call that m. We know that this normal goes through point C. So it goes through the point 3, 10. So the normal goes through there. But that means that if we plug in 3 here, then it must be 10 we get out. Otherwise it's not on the line. So here we can solve for m, and we just get that m is 13. So we know that the normal is minus x plus 13. Then we just have to find the intersection of these 2 points. What happens at this point? This point, the y values of the normal and the line are equal. So we have that the y value for that one must be equal to the y value of this one. We just got the linear equation here we can solve. So we solve for x. So adding x on both sides, so we have 2x, and subtracting 4, here we get 9. So we get that x is 9/2, or 4.5. So this is the intersection coordinate x, but then we can just plug it in here or there to find what the y coordinate is. Here it's simple, so we just take that one. So that's just 4.5 plus 4. This is 8.5. Then we know the coordinates for B. It's just 4.5, 8.5. We can also solve it using vector projection. So that's what we're going to see now. To find B, well, then we just have to take here from the origin the vector up to here. Because we know that this vector going from the origin, so let's call it OB. So this is OB. The coordinates or components of these vectors is equal to the coordinates of this point. So if you can find out this blue vector, then we know what the coordinates of B is. Okay, so then we have to make a plan how to find out what B is, or what the vector OB is. We don't have the coordinates of B, so we cannot find it out directly, of course. But, for example, we know the coordinates of A, so we can figure out what this vector is. And this vector here, if we know this vector, then we can find the blue one just taking this one plus this one. So if we know this pink one and we know this yellow one, then we can just add these two, and then we'll find the blue one. Okay, so this one, what is that? That's A, B. And the pink one is O, A. So, but the problem is that we don't know the yellow one. We know the pink one, but we don't know the yellow one. But then we can use vector projection. If we project this vector, so we project that vector this vector is AC. And that vector we know, because we know where it starts at A, and we know where it ends. So we know the coordinates, so we can figure out what AC is. So if we project this one down onto the red line, then we will get the yellow one. And having the yellow one, then we can just add the purple one, or pink one, then we will get the blue one. And then we are done. So that's our plan. So first we have to find out what AC is. AC, we know that it starts at x coordinate 0 and ends at x coordinate 3. So it goes 3 steps in the x direction. And it goes from 4 to 10 in the y direction. So it goes 6 steps in the y direction. So here we have the components for AC. Now we need to project AC on the red line. But how should we do that? Then we need a vector on the red line. And we can't take the yellow one because that's one we're trying to find out. But we can just take any directional vector here on the red line. So we need this directional vector or any other. But the most simple one is just to take this one 1a, where the slope of this one. And the slope of this one is just 1. So this one is 1, 1. So now we only need to project AC, this one, on V. And then now we have the formula for projection. The projected vector is AB. So the result we get is AB. And the vector we want to project is AC. Then just plug into the formula we had for vector projection. Then we just take AC times V. So you can go back at the formula look if you've forgotten how the formula looks. So there's 1, 1 here, or V. So here is the formula for vector projection. So this is projected vector, this is the vector we want to project, and the rest here is the directional vector on the line. So projecting AC on V. Then we have V squared here according to the formula, and V here again. Then we just need to plug in. So now we know everything. AC is 3, 6. V is 1, 1. And here's the length of 1, 1. And it's 1 squared plus 1 squared, and square root of that, but then it's squared, so those cancel, so you can leave it at that. Then multiply 1, 1. Then 3 times 1. 6 times 1 is the dot product. And here we just got 2. So this is 3 plus 6, 9, half. 1, 1. So now we know the yellow one, AB. So then we only need now to add the pink one to the yellow one. Then we'll get the blue one. So OB, the blue one, that's just OA, the pink one, plus the yellow one, AB. OA, well, that's simple. It's just from origin to this point. So it goes 0 steps in the x direction and 4 steps in the y direction. And AB we have just calculated. Okay, so adding these. So let's multiply in that one. This is 9 half, 9 half. And then we just get 9 half plus 0, that's 9 half. 9 half plus 4, and 4 is 8 halves. So 8 half plus 9 halves, that's 17 halves. Then we know now the blue vector. So it's 9 half, 17 half. But the blue vector has the same components as the coordinates of this point, since they start from the origin. So we know that B is equal to this one. And this is 4.5, and this is 8.5. So now we have seen how you can solve for either using this normal, or I forgot to change the number here, but this was alternative number 2 we did. and it's not the normal, but the vector projection. So you can use any of these two. Now we want to find the distance from a point to a line, to a straight line. So what is meant by the distance from a point to a straight line? We could have any distance here. We'll mean the closest one, and the closest one is the one that is perpendicular. So here we have the normal to the red line is this black one. So we mean the distance here now, we mean this distance here, d. So how could we calculate that one? We will use vector projection to find it. There are different ways you can go about here, but we will use the normal to the red line to calculate it. Let's draw a parallel line to the red one. It will look something like this. Okay, so these two are parallel. If we can find out this vector, so if you can find out this vector here, then we just need to take the length of this vector, then we have the distance. So how can we find the green vector? If we just take now this pink vector, so we take this pink vector and let's project it on the normal. So here I lengthen the normal. So we project the pink one on the normal, then we just get the green one. So what do we need to do then to find this? This one we can find because this point here we can find out. Let's call this point Q. What is that? That's the intersection of the red line with the y-axis. But that's just this value here. So at x coordinate 0 and -3, that's the point here. And this point we have is 1, 4. So now we can figure out the pink one. That's just QP. And that's just from 0 to 1. That's 1 step in the x direction. And -3 to 4, that's 7 steps in the y direction. So now we have the pink one. Now we only need to project that one on the normal. But then we need a directional vector for the normal. So we need this one. And what's the vector components of that one? That's just 1 and the slope of this one. And what's the slope of this one? We have the slope of the line, and that's just a half. So if you take -1 over a half, that is the slope of this one. So this is just -2. So here it must be -2. So now we just project the pink one on this directional vector for the normal. And then we know how to do with the formula we had for vector projection. Again, the vector projection formula was given by this one. So the projected vector we want to get is this green one. Let us call this point here for something. Let's call it R. Then the projected vector is RP. RP is green vector. And that we get by projecting the pink one, QP, on V. So just plugging into the formula. Like this. Then we just have to put in QP is 17 times 1 minus 2. And this is 1 squared plus -2 squared. And the square root cancels with the square here. And then 1 minus 2 again. 1 times 1 is 1. Minus 7 times 2, that's 14. This is 5. This is 1 minus 2. So this just becomes minus 13 fifths. 1 minus 2. Or if you multiply in, (26 fifths). So we have found the green one. This is the green one. Now we only need to take the length of the green one, then we have the distance. So the distance is the length of this one. That's just Pythagoras theorem. So this one squared, but so we need to take the square root. Then it's minus 13 fifths squared, 26 fifths squared. Then what do we get? So this is 169 25ths plus 676 25ths. And let us continue up here then. So this is equal to square root of 845 divided by 25. Plugging this into calculator, we get 5.8. In a moment, now we will see how to calculate it more exactly, but since it's tedious here, let's stop there. So we see that the distance here is 5.8. That we found out by vector projection. You see here that in the end the numbers were quite large. We could have avoided that actually, if we would already here be a little bit observant. So let's just show that. So if you stopped here instead, then we see that we could just have taken the length here is equal to the length of RP. So we've taken length of this one. Then we should take a length of this. And we have seen a rule before that if you take a length here, you just take the length of the number in front. And then you take the length of the vector 1 minus 2. And what's the length of, this is the absolute value, so you just drop the sign. But what is the length of that one? This is just Pythagoras theorem. 1 squared plus 2 squared, that's 1 plus 4, 5. So just square root of 5. And we can cancel out 1 square root here, then we get this. So the exact answer is this one. You see, it's much simpler to do it in this way. The problem is that if you multiply in this and do the Pythagoras theorem, then we get larger numbers. So it's easy just to keep this here. So this is the exact value, but if you round off, you will get this.